Hello and welcome back to Differential Equations section 3.4 on mechanical vibrations. So this is some really cool stuff because we get to apply the concepts from our last class where we talked about complex roots, and we can understand mechanical systems through the equations which we derived last time. So we said that we can have a system which has some kind of a mass m attached to a spring, and if this is the equilibrium position, let's call that position 0, we can pull the object and then set it in motion where the object will be going left and right and left and right. Now, in the case like this, where if we have 0 friction and 0 air resistance, gravity would not impact, well, gravity would impact actually because of the friction. By the way, if you don't understand how gravity impacts horizontal motion is through friction. See, the weight of the object, I'll draw the new picture here. So this is your mass m. The weight of the object goes straight down, right, as a vector, which is the weight. And then that's calculated as m times g, mass times the acceleration. Then you have the normal force, N, which is equal to the opposite of the weight. And that's the normal force in physics. It's in this case, it's always perpendicular, right, to the surface. Sorry, yeah, perpendicular to the surface. But in this case, it's equal to the weight because this is on a flat surface. And if you push the object this way with the force, then there will be a friction force F over here, which is mu kinetic if it's moving, times the normal force. So now you see how the weight impacts the horizontal motion, right? It's trying to slow the object down. The heavier the object, the more of the friction there is, and the more of the friction, obviously, right, then there is more opposition to the motion. This is why trains cannot, do 0 to 60 in 2 seconds, and they can't stop on a dime, right? Sometimes it takes a mile to stop a train or more, right? They're insanely heavy, right? A lot of weight on a train. Now, there's not that much traction, right? They don't have rubber on those big train wheels, right? It's just metal on metal. That should slip a lot. So they do have some systems that spray sand in front and blah, 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 doesn't matter. But the trick is that when it's slippery conditions. But for most cases, the weight is enough to create enough normal force to create enough friction right in between so the train doesn't slip and stays on tracks. So we have the two worlds that we have to understand for this particular lecture. We have a world where you only have a spring and let's say nothing else. So we'll call that undamped system. And then we'll have the one with dampening, which is where you have your object M, and you're going to have a spring on one side. On the other side, you're going to have a dashpot, which is the one that has a cylinder inside attached, and the liquid and so on. So that one slows the system down. So you still have equilibrium, and then the spring will start oscillating when you pull the object, and then the dashpot will make it stop. So these are the two cases that we are going to look at, and we are going to recall the formula from the last class, which is the same formula we're going to use today, which was mx. Maybe I should write this in blood because it's the most important equation for today. Mx double prime plus cx prime plus kx equals to some external forcing. Now, x is the distance function, and then t is time, which is our independent variable. You can see it here. So technically, this derivative here is the second derivative of x in respect to time. That's what it is. And this is your x, right? The distance along the x horizontal surface. So when you look at this, right, this term over here will be called forcing term. And the forcing term is something that we are going to avoid in this lecture, because that requires undetermined coefficients and variational parameters, which is the next lecture. So I believe in 3.6 we will do, yes, forced oscillations and resonance in 3.6, where, again, forced oscillations, meaning you're adding the energy to the system, and right, the system keeps adding the energy from this one, usually some kind of a trig function, right? Because you constantly add, like think of a kid on a swing, right? You don't push the kid all the time, right? Kid shows up on your side of the swing, you push the kids go to the other side. At that point, there is no push, right? And it comes back. So you periodically, right, push the kid. Only when the kid swings to your side, you push the kid, then the kid goes out. So the same thing, you can have the forcing for these things, right? Which could be the forcing of whatever, sine or cosine forcing. But then you can also have just the initial push, right? And that's it. And then the system just goes into its mode and it's going to do its own thing. You don't push it anymore, right? We'll see that with the impulse functions and delta function and a whole bunch of stuff. Anyway, so the goal for today is to take a look at mx plus cx prime plus kx equals to 0, and understand this from the physics perspective, where we don't have the forcing. So I'm just going to box this one because this is what we are focusing here. I'll put here 3.6 so you know that's coming up. And say here no forcing, meaning your f of t equals 0. Now that we have this situation, we can go and take a look at some of these basic motions. So the first part is the first picture on top, which we'll call the free undamped motion. And that will be, you just have your spring over here going into the object with a mass m, right? And then you pull this thing, and then it's going to start oscillating back and forth. So in this case, no dash pot, which means no cx prime term. The only equation that we are looking here is x double prime plus kx equals to 0. So again, no forcing on this side, and in the middle here, the cx prime term is missing because there is no dash pot. We'll see later on that the dash pot is the one that slows it down. So now, when I look at this this problem, to solve this problem, we divide everywhere by m, because we want that coefficient in front to be 1. We get x double prime plus k over m x equal to 0. And for simplicity, now it doesn't look like it simplifies the problem, but it actually does, so you have to wait for it. We'll say omega 0 is equal to square root of k over m. Now, if you do this substitution, your equation becomes this. And we know what we do with the second order constant coefficient equations. we convert it to r. And when we convert this to r, we know we can solve it and come up with r equals, right, the r equals, and all you're going to have is plus minus I omega 0. Remember, when you move this to the other side, it becomes negative omega 0 squared. When you take a square root of that, the negative spits out an I, and then cancels the root cancels the square, giving you just omega 0, right? So that's the basic algebra on the side. And this gives us that good old solution, x of t, which is what I had before we started the class, of a cosine omega 0 t plus b sine omega 0 t. So this is the argument, right, of cosine and the argument of sine. You don't need these parentheses, like because we know that t is the variable, so you have to have sine of t. And then if you put a constant in front of it, right, it's the one that works together with the with the period. So we have the general solution, right? This would be the general solution. And depends on, you know, how well you know physics so far, or if you learned any physics before, you might know that this omega 0 is called angular velocity. It's also known as a circular frequency. Has a couple of different names, but it's in a sense of how fast something is spinning. Because when you're spinning, you're covering the distance, not the distance in a linear sense. You're covering the distance in the angular sense. So the kinematics works in a circle, and then your distance becomes theta. Your speed, velocity becomes omega, which is what we have here, and your acceleration is alpha. You're using those three. The equations are exactly the same as the kinematics on linear. They're just using the angular, right, as the angular motion as the input. So now let's take a look at this motion and see if we can rewrite this in a different form, because it seems that we could somehow compress this into a single trig function rather than having cosine and sine together. So let's take a look at the witchcraft that would give us that. So if you go and you make a triangle with sides A, B, C, and some angle alpha in it, you can write sine alpha is opposite over hypotenuse. You can write cosine alpha is adjacent over hypotenuse, and obviously you have your Pythagorean theorem for the whole thing. So these are the three standard equations that you can write for any right triangle. My triangle doesn't look too great, but hopefully you understand. And now, as you can see, I can solve these for A and B, and they would both be in terms of C. That means that I can combine these terms into one term. Wow. So I can write from this equation, I can write that the B is equal to C sine alpha, and from this equation I can write that A is C cosine alpha, and I can plug those in, right? So if I plug them in, my x of t solution becomes, instead of A, I have a C cosine alpha cosine omega 0 t, and then plus, and instead of b, I have c sine alpha, and then the rest is sine omega 0 t. And if you carefully look at this, you quickly realize that this is that formula. You can factor out c, right? This is the formula for a sum of two angles under the cosine. So this becomes c cosine of omega 0 t minus alpha. And because you have this, technically the formula would be alpha minus omega 0 t, which you can write as negative omega 0 t plus alpha. Then you factor out the minus omega 0 minus alpha, but the cosine is even function that would kill the minus. So for those of you who are really good with trig and really good with mathematics, you pick that up immediately that I had them in a wrong order. If I have them in a wrong order, it's a cosine, it doesn't matter, because once you factor that minus, cosine is even function, it kills that minus anyway. So I would be in trouble if it was a sine, but because it's a cosine, I just wanted to point that out. So here is your new form of the answer, where your c is given as a square root of a squared plus b squared, right? And your alpha is going to be inverse tangent of opposite over b over a. B over a. So now, when you get a solution of when you get a solution in terms of those a and b, you can actually collapse that answer into a single trig function, which is why we see that motion just oscillate, right? The motion would just oscillate. And we're going to have c represent the amplitude, and that would technically be how far out the object oscillates, right? So if you have a spring that pushes the object left and right, how far to the right, how far to the left from the equilibrium position the object would go. That's measured by c. And then you also have omega 0. This is how fast it's moving left and right. So not how far it goes, but how fast it goes. And that's constantly changing, obviously, because it should be going the fastest as it's going through the origin, and then starts slowing down because the spring is opposing the motion. Then it reaches the end and it's 0, and then spring starts accelerating it, again going fastest, hitting the equilibrium 0. Then the spring starts stretching beyond its natural equilibrium point, which means it starts slowing down the object, but the object is under inertia, so it's moving still forward, but it keeps slowing down until it reaches the other side. Then its speed is 0 again, and then the spring pulls it back in, accelerating it, so it goes back and forth, back and forth, back and forth. And again, without air resistance, gravity to create friction and so on, this object would oscillate back and forth forever. And we see that that oscillation happens, right, because it's a cosine solution, right? So the omega 0, this is not a W, this is omega. It looks like that, right? It's round and wide in comparison to W, that it's pointy and straight. So omega 0 is circular frequency also known as angular velocity, angular speed and stuff like that. And then alpha is the phase angle. Now this one also creates confusion. We'll see later that when the phase angles, you have to have the same phase angles so that there is no interference in the motion. The alternating currents, for instance, depends on where you are in the world, the 50 hertz or 60 hertz, which means it switches the polarity 50 or 60 times per second. Your battery has the standard polarity, it's a direct current, so plus is always on one end and minus is always on the other end. And you have to plug those batteries the right way into your device, and the device will work. So you always have to look which way you turn the battery, because the plus and minus. Now for alternating currents, it actually doesn't matter, because alternating currents switch the polarity 50 or 60 times per second. So there is no right way or wrong way to plug something into alternating current outlet. So this phase angle is going to be important, because it deals with the latency and the frequency and all of these kind of things. And then if you are turning on additional, let's say, generator to produce more electricity, if it's out of phase, the whole thing blows up. Now that's all going to be talked about later. We don't have to worry about it now, but when we start talking about the resonance and why soldiers are not allowed to march over the bridge and so on, how do you use your singing voice to break the glass, which is perfectly possible, right? You will figure out all of those things. Now you can come up with the formulas for period, which is T equals 2 pi over omega 0, and frequency, which is given as 1 over the period, which is obviously omega 0 over 2 pi. Now, again, think of the word period and what it means, right? When you do something periodically, you go periodically to the store. You don't live at the store. You're not there all the time. You go once a week or twice a week, right? So the period of time, this is given in, let's say, seconds. Now, frequency is 1 over second, which is actually labeled as hertz. And that is how frequently you go to the store. So period is how long, I guess, in between those trips, and the frequency is how often you go to the store. So you go twice a week, let's say, whatever. So the period is the period of time, and the frequency is that instant of, as I said, let's say switching, right? So the polarity of alternating currents switches 60 times or 50 times per second. So there are 50 switches happening in a second. So that's what we have to understand our basic ideas. And now we want to take a look at a simple example and understand some of these calculations, in a physical environment. So let's say you have x double prime plus, let's say, 36 for simplicity, x equals, not prime, x equals 0. And you want to take a look at the solution for something like this. So we solve our r squared plus 36 equals 0 on the side, and you get r equals plus minus 6i. That immediately produces that solution x of t, which we studied last class, of a cosine come on tablet, cosine 6t plus b sine 6t. So now we know that our omega 0 is 6. If I know that, I can instantly calculate the period, which is 2 pi over 6, which is pi over 3, and I can instantly calculate the frequency. Now let's say this is in seconds. And then I can calculate the frequency, which is always 1 over t, which in this case is 3 over pi, and that would be hertz. So I immediately have the period, pi over 3, that's about 1 second. Now, what that means is that this motion repeats roughly every 1 second. I know it's 3.14 over 3, right? So it's like 1.04666666 going forever, right? But call it roughly 1, right? So what period means is that this particular motion in its entirety repeats roughly every second. So if it takes the object 1 second to go and back to its position, roughly 1.4 seconds, or let's go with a 5, right? That's approximation. So it will take this object about 1.05 seconds to do this one loop. Then it will take another 1 point, right? And then another 1 point. So that's what the period means. And the frequency is just 1 over that value. So if you go and flip this and you say 3 point divided by 3.14, then that's going to be 0 point, right? And you go 9, blah 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 blah, right? So you can get the value for the frequency, and that's how many switches occur in the whole motion. Now, for our purpose here, right, we do not have initial conditions to calculate A and B, so I cannot calculate C and alpha, right? We were only able to calculate omega because I need to have A and B so I can compute the C and I can compute alpha to push them together. So I just want to quickly check if we can have a problem that will have those, so we could calculate stuff. Let's see what we can do with the problem number 4. It says a body of the mass of 250 grams. Great. We need to do the problem in kilograms, right? Which means mass is 1/4 of a kilogram. 1 kilogram has 1,000 grams. 250 is 1/4 of 1,000. So 250 grams is 1/4 of a kilogram. Is attached at the end of the spring that is stretched 25 centimeters by a force of 9 newtons. So at time t equals 0, the body is pulled 1 meter to the right, stretching the spring and set in motion at the initial velocity of 5 meters per second. To the left, okay, and find everything. Get all. All right, cool. So when you start a problem like this, you have to understand that if you do not convert units to their base units, meters, seconds, kilograms, newtons, and feet, pound, second, and the whole numbers are not going to work well, you are going to get the problem wrong. Even if you do the correct procedure, your problems are going to be wrong because your units brought in the wrong numbers. So we are not going to use 250 grams. We're using 1/4 instead, because the kilograms are unit for mass. Gram is the unit, but it's a smaller unit, just like feet and inches, right? And if you say feet per second and someone gives you inches, you have to convert inches into feet so you can have your feet per second. Same thing with miles per hour, right? You can't put feet or inches or anything in there. It has to be miles. So in this case, you are working with meter, kilogram, second. And any other measurement is automatically has to be converted. Otherwise, doom. So let's do all the unit conversions. I have my mass as 1/4 kilogram. That's a win. Then for the spring constant K, if you remember, the spring constant K was involved with calculating the Hooke's law, right, which was force equals K times the distance covered. Well, my X of 25 centimeters is no bueno, right? We have to convert that to meters. So 25 centimeters is 1/4 meter, because 1 meter has 100 centimeters, which means 25 centimeters is 1/4. Therefore, it's 1/4 meter. And 9 newtons. Okay, finally something that I don't have to convert. Now, that could have been kilonewtons, could be, whatever. In that case, you have to convert it. But if the force is given as 9 newtons, and because it's given as 9 newtons, we leave it there. So we have our force. And now we can stuff all of that here. So 9 is equal to K times 1/4. So we got K is 36. Oh, isn't that lovely? It's going to be exactly the same as the problem we did here, right? Because I got 36. All right, now we get to our initial conditions. We see that here it says initial condition at t equals 0. We stretch it 1 meter. Now, what was the velocity? Oh, the derivative of x, right? The velocity of 0 is given as 5 meters per second. Okay, good. Those units I don't have to convert. It's given in meters per second. Could have given me 2 kilometers per hour, because if you are using those, let's say you're using the thing that cops use to clock your speed, that shows miles per hour and kilometers per hour in all other countries. So if you use that to clock the speed in kilometers per hour, you have to convert that into meters per second, sorry. But meters per second are given, so we're all cool there. All right, so I have my 4 pieces of information. Here's the mass, here's the K, and here are the 2 initial conditions that I'm going to need later to get those A and B. All of that in the word problem. So now, stare at the screen, look at all of these numbers, and I'm going to read the problem one more time. A body with a mass of 1/4 kilogram is attached to the end of the spring, whose coefficient, right, constant, is 36 newtons per meter. At the time t equals 0, the body is pulled 1 meter to the right at the velocity of 5 meters per second to the left. And get all. So calculate, get the equation of the motion, get literally everything. Well, not a problem for us, I hope. We have 1/4 times x double prime plus 36x is equal to 0. Right? So now we are going to multiply entire equation by 4 to just get the front coefficient to be 1, plus 4 times, so we have 4 times 30 is 120, 4 times 6 is 24, so 144 x equal to 0. Now, r squared plus 144 equals to 0, and r equals plus minus 12i. That gives us our initial general equation, right? X of t equals a cosine 12t plus b sine 12t. Cheap and easy, right? Now I have to use my conditions to calculate a and b. So I need the derivative, which would be 12a negative sine 12t plus 12b cosine 12t. Now use my conditions. For x of 0 equal 1, I have the first equation, which is 1 is equal to, when I plug in 0 for cosine, cosine survives, so a times 1, plus when I plug in 0 for sine, sine dies, right, because it's a 0. So from here I calculate that a is 1. The other condition for velocity that was given, which is x prime to be a 5, is the second line. 5 equals, now when I plug in 0, negative 12a will be multiplied by 0, that term dies, plus 12b times 1, because cosine of 0 is 1. So from here we can calculate that b is 5 over 12. So I have a is 1 and b is 5 over 12. So now I have the x of t equation given as cosine 12t, because the a is 1, plus 5/12 sine 12t. Now this equation is technically, mathematically speaking, we're done, right? Mathematically speaking, we're done. You have your particular solution, you calculated your a and b. However, engineers don't like it, right? Because it is not easy to see a single oscillation from this form, right? There's nothing that tells me that this motion is just that when I look at this, because I see cosine plus sine, right? They are moving at the same speed, they're both 12, but I would like to mush these together. And we achieve that by figuring out c, which was the square root of a squared plus b squared, and that is the square root of 1 squared plus 5 over 12 squared. Now that is 1 plus 25 over 144, which will give us 144 plus this one is 169. Okay, so square root of 169 over 144, and that turns out to be 13 over 12. This is a really nicely, worked out problem. So we actually have all these numbers work out without decimals and stuff like that. So that's awesome. And I think I'm done here. Yes, good. Now, the alpha angle, right, the phase shift, was the inverse tangent of b over a, which is just actually inverse tangent of, because a is 1, right, is just 5 over 12. Right, and you could do that on your calculator. This is a 5, 12, 13 triangle, which is called the Pythagorean triplet. So in a good old day, people had this all memorized. Let's see what we get. Okay, so I'm getting 22 degrees, well, roughly 22.6 degrees 22.6 degrees. So I can write this as x of t equals 13 over 12 cosine 12t minus 22.6 degrees. You can also write that in radian measure if you want. But since this is, engineers answer, engineers love degrees, not radians. So mathematics uses radians all the times, and engineers would use degrees as the answer. Now, obviously, if you plug in degrees answer in your MyMathLab and it tells you it's wrong, and then you try to use radians and it takes it, then it's just the fact that MyMathLab is the mathematical software, so we prefer radians. But engineers prefer degrees, and being that maybe one or two of you at most are math majors. Guys, you should all sign up for a math major if you are engineering majors. It's just a couple of extra courses, one or two extra courses on top of what you take to take the second degree. So it's a no-brainer to take one or two courses. One is a math course, and the other one is a programming course. So, it's very, very easy to dual major and in today's age. So much overlap between the two programs. So because of that, right, we can have more mathematicians actually in a course than you, but primarily you guys are engineers, and the answers you like to see are primarily degrees, right? But that's what we is. So that's it. That's what we have for free undamped motion, and we just have one more case when we add that C in with the dashpot and try to analyze the situation using the slowdown, right, when it eventually slows. Now we can see from this model before I go to the next one, we can see from this model that this cosine here, right, will just make it oscillate forever. And that's due to the fact that there is no term in the equation to slow it down. And then in the concept, we said that there is no term that slows it down because it was just free undamped motion. Now, we go into the other part where we are going to have this C back. So we have our mx double prime, which is the second derivative, plus cx prime plus kx, still equal to 0. Again, we're going to change that in 3.6. Today's lecture is just going to get the forcing, and it's going to make a lot more mess. All right, so now we are going to divide everywhere by m again as before. And now we are going to make a couple of substitutions. The good old omega 0 as a square root of k over m, that doesn't change. The new one is that this c over m business that we have in the middle is going to be now called 2p. Now you would go like, why? Well, the same reason. Later on, equations work out nicer if you have 2p. It simplifies much nicer. So, yeah. And it is time for us to now solve this new case that is just simplified x double prime plus 2p x prime plus omega 0 squared x equal 0. Now, it all looks like unnecessary stuff until you go into r squared plus 2p r plus omega 0 equal 0. And you are supposed to solve this quadratic equation. Now, you use the quadratic formula, the negative b plus minus blah, blah, blah. The algebra should work very nicely for us in this case. So let's see where would that equation take us, right, when we use that quadratic formula. So the r should be equal to negative b plus minus square root of b squared minus 4a. Oh, I forgot the square here. 4ac divided by 2a. So this is your standard formula, quadratic equation. Nothing special, nothing weird. We are going to have our negative 2p plus minus the square root of, and I'm going to have over here 4p minus 4 omega 0 squared divided by 2. And hopefully now you see why we did what we did. Negative 2p plus minus, when you factor 4 and you kick it outside, it becomes a 2 square root of, and you have your p minus omega 0 squared divided by 2. And this is where these 2, when you factor it, they cancel. So the r becomes negative p plus minus square root of p minus omega 0 squared. That's it. There I say just that. Now, what is happening? What is happening here? I see now that I forgot this square. When you square b, that's your 2p squared is 4p squared. I forgot that square. True. So please go into every root and add that little square. That's very important.
You noticed it, but then you forgot you noticed it.
Okay. Yeah, but I noticed here at the end. I definitely noticed here because I need 2 squares there, so all of this can work out. Now, because now we're going to plug in those c's and m's and stuff like that, and I need p to be squared in order for me to be able to work this stuff out. So so we have our r's, right? R1 would be 1 with a plus, and R2 would be 1 with the minus. Now remember, in order for this to be oscillation motion, right, the p squared needs to be bigger than omega squared, right, to give us, sorry, p squared needs to be smaller than omega squared to give us a negative number, so that we can have the negative, give us the complex solutions, right? So if we just yank this p squared minus omega squared business outside, and we plug those values from before in, so p squared minus omega squared, what would happen? So what was p, right? If you remember, we said that c over m was 2p. So move this 2 to the other side, it's going to be this, right? And then when you square both sides, it's becoming c squared over 4m squared. And then minus, and what did we say that omega was, right? It was k over m, right? So omega 0 was square root of k over m. So when I square both sides, it will just kill the square, and I'm just going to get it k over m. and just do the common denominator, basic algebra of 4m squared. We have c squared minus, and now over here I need 4m, so 4mk on top. All right, cool. What did I achieve with this? Well, first of all, remember that you want this thing under the radical to be negative, and you have it equal to this. Notice that the denominator is always positive. Mass can only be a positive number, and if mass is a positive number, right, then times 4 and squaring it, obviously. I mean, you don't even have to look into physics. You can just say, oh, number is squared, that's always positive, times the 4, which is always positive, so denominator is always positive, I don't have to worry about it. So clearly, the entire calculations up there is that the c squared minus 4mk needs to be less than 0, which all means that the c squared needs to be less than 4mk. Like, otherwise, you do not have oscillations. So if c squared is smaller than 4mk, you are going to get your oscillation. So now, see, designing a dashpot can give you 4 solutions. One solution is going to make it so your solutions are, there's no oscillation at all. The dashpot just instantly stops the motion as soon as you set it into motion, because c squared would be bigger, right? So we need this for oscillation, right? That's what we need. Now, I am still going to mention the other 2 terms. There are two cases that are not interesting. C squared bigger than 4mk, that's the 2 real roots, equal no oscillation. C squared equal 4mk, that's the 1 repeated real root. I hope you guys remember this. Also equal no oscillation. And finally, the case that we care about and we want, c squared less than 4mk, or km, whatever, is the one that has 2 complex roots, equals oscillation, which means that we are able to have this. Now, the fact is that you are going to get a solution that dies out in time. So you are going to have your solution, if this is the case, and this is the case that I'm going to box because this is what mechanical engineers care about. I mean, they care about the other 2 as well, but this is the one that gives you oscillation as a motion. From here, you get your x of t equals the good old solution, what was it? E to the negative pt cosine, a cosine omega 0t plus b sine omega 0t. So that's your solution that we learned before. And then you get to deal with your the calculation for a and b, and right, if you have initial conditions, which can further be simplified into x of t equals to e to the negative pt, and then you can have the value c, that, well, actually I should put that c in front, and that's going to give you a over c cosine omega t plus b over c sine omega 0 over t. There we go, omega 0 t. And that now turns into, finally, that CE negative PT. Remember the cosine of omega 0 t minus alpha? So it can be all compressed into the single formula, which is our goal, where we have our standard C is a squared plus b squared. Alpha is inverse tangent of b over a for the purposes of writing the solution. And what is the most important part here, if you're looking at this from perspective of physics, and you should always look at it that way, is that here is the term that kills the motion eventually. So before, there was no friction, there was no air resistance, there was nothing there, and the object went left and right, left and right, left and right for forever and ever. But now, if you are measuring your distance x in time t, and it's a cosine, so let's say you start here, it goes down, bounces up, and every time it goes to the other side, there is a less of a bounce. And that is governed by this dying e to the negative p, right? This curve here is e to the negative pt. That's the one that kind of kills the cosine eventually, right? Going to infinity on this side, it's going to give us the 0, right? Which is where the object actually stops. So now we can go and say, oh, the limit as t goes to infinity of ce to the negative pt times the cosine of omega 0 t minus alpha. This part is always going to oscillate between -1 and so -1 and then the cosine thingy and then 1. But this part goes to 0. So when you multiply any number from the range over here, when you multiply any number by 0, the limit is always 0. That means that this object eventually has to stop, right? Eventually meaning, you let it go to infinity, right? Time equals infinity. It might stop in 2 seconds. It might stop in 2 years, but it's guaranteed to stop because this e to the negative pt will kill it as it goes. So now we have, right, the again, circular frequency omega that's read into the worked into the problem. You still have your period and frequency and all of that stuff. Is just that the amplitude of the problem, right? How far the object goes out, dies out as the time goes on, and the object stops eventually. So that's the physics of mechanical vibrations, and without forcing, we can't really go any further in exploring this, but we can always jump into a homework example and work it out. They have really beautiful graphs in the book. I just hope you guys read the book because there's a lot of good stuff in there. I'm going to leave you to read the examples that are worked out in a book, and I'm going to work out literally whatever. Problem 20 is fine. They give you that the mass is 2. They give you that the C is 16. They give you that K is 40. They give you that x0 equals 5 and velocity 0 equals 4. Now, since they don't give any units, we don't have to worry about the units, even though, right, I would call this a lame example. Obviously, if you read the text, you should eventually run into, right, the situation. Anyway, What is the equation which we derived last class, which you are supposed to memorize? Well, it is mx double prime plus cx prime plus kx equal to 0. That's the equation that you are supposed to memorize. And you're also supposed to know that these your initial conditions are x at 0 is 5 and x prime at 0 is 4. That's what it means. X prime is a velocity. Now, since we don't have to worry about the units, we can just plug the numbers in and plow through calculations, right, the best we can. So we have 2x double prime plus 16x prime plus 40x equals 0. Divide everywhere by 2 gives me x double prime plus 8x prime plus 20x equals 0, which further gives me r squared, to do the pirate voice a little bit, r, there we go, plus 20 equals to 0. And now we go and we calculate our r1 and 2. That's going to be negative b plus minus square root of b squared minus 4ac divided by 2a. This is negative 8 plus minus square root of negative 16 over 2. I'm loving it, right? Because that's a negative 16. The square root is 4i. So I have negative 8 plus minus 4i over 2. Gives me the r's to be negative 4 plus minus what? 2i. There's the e part. There is the omega part for my solution. So my x of t is e to the negative 4t a cosine 2t plus b sine 2t. We know what the solution looks like the form of the solution. We know what it looks like. So we just plug those numbers in. So now, all we need to do is differentiate this, hashtag product rule, right? Differentiate this, and then use our initial conditions to calculate A and B. And then once we have A and B, we can go get the C, get all of that stuff, and sort out into that simplified form, right? In the phase form. So x prime of t is going to be copy the first, derivative of the second, so that's negative 2a sine 2t plus 2b cosine 2t, plus copy the second and derivative of the first. That's going to be negative 4e to the negative t, and then copy this mess. Okay. That was a product rule from Calc 1. I hope that is not going to trip anyone. And now we have our two initial conditions, right? The initial condition for the top equation is x of 0 was 5 or 4. What was it? 5. And over here, x prime of 0 is 4. So now plug those everywhere. We have 5 is equal to e to the 0 a times 1, because cosine of 0 is 1, plus b times 0, because sine of 0 is 0. So that's our top equation. It simplifies quickly to 5 equals a. A equals 5. Because, right, e to the 0 is 1. This whole thing is a. A times 1 is a. So a is 5. Good. Done. So A is 5. Now what's happening for the prime equation? I have a 4 over there. Now we have to be careful, because now we also have A working with cosine. And that means that's going to survive there. But luckily we know what A is. So that's going to help us. Let's go. 4 equals e to the 0. Now, in this case, I have negative 2a sine of 0 is 0 plus 2b cosine of 0 is 1. Minus 4 times e to the 0. Now, a is 5 times cosine of 0 is 1 plus b sine of 0 is 0. Clean up the mess. And what do we get? So we don't have to worry about this term. 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 So what do we worry about? Well, we worry about 2b minus 20. That's what we worry about, because negative 4 times 5, that's the only thing that survives. And guys, e to the 0 is 1. So this whole thing over here is just negative 4, and you have that as 5 plus 0 in this. So that's negative 20 altogether. All right, so now that I have this negative 20, that's going to mean that the 2b is equal to 24, and then we have b is 12. So now I can write my particular solution as e to the negative 4t, a was 5 cosine of 2t plus 12 sine 2t. And there you go. That's it. So now I know what a and b are, and I can mush them into that c, right? Because c was a square root of a squared plus b squared, and that's going to give me 13 at the end. And I also have my inverse tangent, which we had the 12 over 5. Was that the same 22.6 from before? 22.5 over 12. 5 over 12. This is 12 over 5. So that's the 90-degree complement, because you are, when you flip, right, in a triangle, if this is your 5 and this is your 12 and this is your 13, if this angle here is 22.6, then this angle over here has to be 67.4. Whatever. So that's going to be x of t equal to 13 e to the negative 4t cosine of 2t minus 67.4 degrees, or put it in radians. There it is. So that would be the solution of our differential equation for the motion, right? And we are able now to, from that point, right, we are able to compute everything. Ta-da! That's it. I hope you're not disappointed. The homework will open on MyMathLab, and yeah, so join Zoom so we can talk about the exam for the rest of the period. So we're going to take about 5 minutes break. Those of you following on YouTube, Join in on Zoom if you want to be the part of the exam discussion for the rest of the class. I will see you later. Bye.